Am I in presentation mode? Did I manage to move to presentation?
Actually, if you want to, just use
there
your
I
present.
Go. Okay, so it's really Algorand in a nutshell. I've never. First of all, you can see the first slide was prepared. Am I with you?
You know, Tal, you kind of come in and out. I wonder if you turn off your own video, that might help, of your face, and then we just see the slides. I believe that's correct as far as.
You see the slides and you hear me?
We see the slides, we hear you, but you kind of come in and out.
Yeah, because somehow, I don't know why. Okay, let's hope it'll be okay. So this you can see was prepared by PR people, not by me. The next slides are not going to be so nice. So of course, Algorand was founded by Silvio Micali, whom we all know. The great things about the Algorand blockchain is that it's carbon neutral, it's very fast. I'm going to talk about that. Transaction costs are low, and there is never a fork. I'm going to talk about that as well. We have a lot of programs going on, which if you have students and people who want to get into the blockchain space, they offer a lot of money, and you really can get wonderful funds. That also applies to faculty. We just recently, this past week, launched the ACE program. ACE is Algorand Centers of Excellence, and they're intended for universities to submit proposals doing research in blockchain. This is 100 million algos. Of course, the amount in dollars changes daily, but that's 1.7, let's say, $170 million as of this morning, so a lot of money. There are also grant programs. Those are very nice grants. You can get up to $300,000 for proposing works. This program is also very highly funded. And if you're interested in starting DeFi initiatives, there's also a DeFi fund that you can apply to, but a lot of money all around for things that are not, you can actually do research on the first two programs if you submit something that interests Algorand. So now to go a little bit to the magic of Algorand, to the protocol, which of course, given that it's Silvio who started this, you can imagine is a beautiful solution to a problem. First, what is a decentralized ledger? Maybe everybody knows, but basically it's sort of a blackboard that's standing in the center of town that people can come and write messages on. They're completely sorted and it can never be removed once a message is put on the board. But how do we do this in a decentralized ledger? So these are the blocks. You want to add blocks one after the other. And this, of course, to anybody who's in distributed knows that this relates directly to the question of Byzantine Agreement, which has been studied since the 1980s. I want to say something about blockchain technology in general, from the original Bitcoin solution and to more advanced protocols. What in my mind is nice is that it's taking theoretical work that we've worked on for 50 years and really bringing it to the practice and combining it in beautiful and imaginative ways. And I think that this is the greatness of this area for people like us who are researchers in these on these topics. And so these were sort of Byzantine Agreement is really a private, yes?
The slides don't seem to be advancing.
Which one are you on? Do you see Byzantine Agreement?
No, we are on the second slide with Silvio's picture on it.
Oh, it is the best slide, but when we see Silvio's face. Now, are we on the right page?
Yeah, it says Byzantine Agreement.
Okay.
Yeah.
Okay, I think I'm having problems, but okay. So basically, these are sort of private blockchains, you can think of them. And the breakthrough that was introduced by Nakamoto is how do we make this into public blockchains? How do we allow the whole world to participate in order to maintain the ledger? Which, of course, the Byzantine Agreement protocols run in time at least and cubed in the number of participants. So how do we do it if we're talking about millions and millions of participants? How do we do such protocols? And the idea that Nakamoto has is that we would do some leader election, and that was done via proof of work. And basically, there was a puzzle that was put out, and that miner guy there sort of solved the puzzle, and then it was given the right to add the next block to the blockchain. But the result of the fact that it's a proof of work means that it takes 10 minutes to create a block. The puzzle is very computational intensive. For various reasons, there are only 2,000 transactions per block. And this also causes there to be high fees. Of course, because it's so labor intensive, the electricity consumption is extremely high. And de facto, instead of, the idea was that it would be a very decentralized system. De facto, it's very centralized because mining farms were introduced, and today it's thought of that there are really only 3 mining farms, 2 of them in China, so not very decentralized. And there's an additional issue, which I had mentioned on the first slide that was prepared by the PR people. There's also an issue of forking, that sometimes the blockchain can split, and then somehow you need to converge, but there is a potential for forking. And in fact, the fact that there's a potential for forking also causes this huge delay between the time a transaction is submitted to the time that it's accepted, because you want to know that no fork occurred. So it's a problem. Let me skip this because I want to go faster. So the idea is, and this is where this ingenuity of Silvio comes in, is he said, why are we not doing something better for the solving of the puzzle? Why does the puzzle have to consume so much work? And in order to solve this thing, he introduced cryptographic sortition. And as I said, what's beautiful is that theory again came into play, and ideas that had been around for a long time were introduced for this cryptographic sortition. And anybody who's a little bit familiar with the cryptographic work literature, it's basically a verifiable random function, which was introduced in a paper by Mikhail, Rabin, and Vadan in the late 90s, early 2000s, and incorporated in a magical way into this thing to substitute the puzzle work with something much faster. So here, basically, this is the certificate here on the left. This is what is given out as a result of the computation of the VRF. It's extremely fast. And you compute it locally, and you can do it. Yes.
Tell your slides are still Byzantine Agreement.
Oh my God. Oh my God. Okay. So you missed all my beautiful.
Okay, now we see fork in the road.
You know what? How about I leave it like this, and can you see this?
Sure. Yes.
And I won't go into presentation mode. Okay, let me do this quickly, just so all my artwork will not be lost. Okay, right. Here you can see quickly. Oh, look at this beautiful slide. Quickly. The fork. Here you see the fork, and these 2 I skipped. And here I spoke about the fact that Algorand uses the sortition. And here is how the certificate is created, which is via the VRF. But that was not the only problem that I said in Bitcoin, that it takes a long time to prove the puzzle. It also takes it still has the possibility of the fork. So then, of course, is what do? And we have these solutions of Byzantine Agreement that come into play again. And the idea is that in Algorand, you do both the cryptographic sortition, which is based on the VRF, which gives you the leader quickly, but then you also add on top of it a very, very fast Byzantine Agreement to eliminate the possibility of the fork. So those two things combined give you the Algorand protocol for the creations of the block. And what is the result of this? That you go down from 10 minutes to 5 seconds. You go up from 2,000 transactions to 5,000 transactions per block, and you can offer low fees. Electricity consumption there is electricity consumption, but effectively nothing. And it also eliminates those pools, because why were the farms created? Because it's very labor intensive. So you sort of pool all your resources together. But here in Algorand, actually, every person who buys algos can participate in the block creation proportional to the number of algos that they have, which is the idea of proof of stake. According to your stake, you get to participate. And this eliminates the chain and the forking, and you have immediate finality. Okay. So now I want to say something a little bit more researchy, which I didn't prepare in the slides. The Nakamoto model had a new idea for computation, sort of for protocols. Every party speaks only once. And this helps against corruptions, and you don't know who's going to be speaking. So if I'm going to be the next person preparing the block, until I propose the block, I don't speak. So nobody knows it's going to be me. And this helps against attacks. Silvio took this thing to the next step and managed to create a Byzantine Agreement protocol where people need to communicate based on prior things that they had seen in the protocol. But he managed to transform it yet again to a protocol where each party speaks only once. And this was wonderful. But in the Byzantine Agreement protocol, parties don't have private information. So it's easier to do. But in our group at Algorand, what we did is we took it to the next level. And whoever knows what multi-party computations are, they're protocols where many people participate. They also have private information. And even with this private information, we managed to give solutions that enable each party to speak only once. And it sort of started with very theoretical work, and now we're really pushing it to implementing it and possibly getting it on our blockchain in a future time. Okay.
So
and
Cal,
yes,
Cal, you just have like 1 minute, I'd say.
I'll be done.
Sorry, thank you.
Okay.
I know this is super interesting though.
No problem. So, so we have all these, the blockchain has on top of it all kinds of layers of operations. And in our layer 1, we can do a lot of things on the blockchain already. And our layer 2 has actually very advanced smart contracts. We have a lot of things running with standard assets, which is sort of something, if you want to build on it, you create your own token and you run it. And also DeFi projects are starting to emerge. And if you want to get started to building an Algorand, here are links. And I will share this presentation and anybody can have access to these things. And again, I'm reminding of our big projects with all that wonderful amount of money for anybody in the research community to access. That's it. Thank you.
Awesome. Bravo.
Thank you, Tanya.
That was great, Tal. Are there any questions? If there are questions, you can raise your hand or you can put in the chat, I have a question and we'll call on you. But I don't see any hands raised right now. But then again, let's see. Yeah. Okay, thank you. Thank you, Tal. I think, Prasad, I think we can proceed.
The next speaker is Reena Panigrahi from Google.
Wasn't it someone else in the before me?
No,
I
I
was
don't.
okay.
Yeah, go ahead, Rita. Thank you.
Okay, can you see this?
Yes.
Yes, we can see it.
And is it advancing fine?
Yeah.
Perfectly, thank you.
Yeah, so I'll be talking about what are some potential data structures that could be used as abstraction of the mind. So we're constantly faced with sights and sounds, and we try to make sense of it and make predictions and take actions. And is the mind like some single giant deep network, or is it lots of modules? How is memory implemented? So if you just meet someone over coffee for a chat, how do you remember who was the person, what was roughly talked about? And more importantly, if we were to meet the same person again, how do we retrieve that information about the previous meeting so that we use that for our next one? Is there some kind of an knowledge graph in our mind? And we're not looking for physiological understanding, but abstract algorithmic understanding. So one thing to note is that if we close our eyes, we can approximately visualize scenes and sounds from the past, which means that we probably have a sketch, store some sketch in our mind that is approximately can reconstruct the event. And it seems to have this, our memory seems to have this graceful erasure property. That means we don't forget things suddenly, but gradually, where we still remember high level details. And perhaps at a logical level, an abstract level, we have many modules in our mind. For example, you can have something for driving, for hiking, for recognizing people, for sounds. And at any one point of time, we're probably only using a few of those modules. Like in a meeting with someone, we're just using the speech recognition module to analyze the speech and the visual recognition module to find people and output people embeddings. So more generally, we might have this modular network which are connected by some edges. And at any one point of time, only a sparse skeleton of modules are firing and producing embeddings for the next level module. And when we want to sketch this, we want to essentially record which modules fired with what values. And there's a very simple way of doing this using subspace embedding. So pretend for a moment that all the modules are just at one flat level of hierarchy like this, like thousands of modules, and only a couple of these are firing, like the person recognition and the speech recognition one, with some non-zero values, with some vectors coming out of those. And to record this, all you do is you hit each module's output with a random matrix, a separate fixed random matrix for each module. And then you add up all these and you get the final sketch. And as long as the dimensionality of the sketch is sufficient to hold the information from each of the non-zero modules, you can use that final sketch to actually recover exactly which modules fired with what values. And this is basically a type of sparse encoding and sparse recovery. And you can think of each module as outputting an object of a certain type, and the type information is being encoded in a specific subspace or a specific direction, which is given by the random matrix. So it's giving an object-oriented view of the final sketch. And it maps events into sketch space where similar events have similar sketches. So if I were to meet someone again, I'll probably get the same modules firing with almost the same values. So I will get similar sketches. And also it can be used to infer to learn new concepts. For example, if I've never seen a tiger before, and if I start seeing a few tigers, then the sketch of a tiger in terms of the previous level modules will all form a small cluster. So when I see a new cluster, it's time for me to understand that there's a new concept here, and I need to allocate a new module. So this essentially gives a sketch over our life. As we collect more and more events, we get a repository of sketches, which forms a knowledge graph. And the edges are just implicit edges, which are saying that these two sketches are similar or related. That's why there's an implicit edge. And there's a modular network that is constantly interacting with this knowledge graph. And so if I meet someone again for coffee, I can use this knowledge graph to retrieve the sketch of the previous event and use that to decide what I do next. So we get a sketching mechanism that gives sketches that are related, similar if they're almost the same events, if they're similar events. And the sketches can be used to approximately reconstruct the original event. But if the event has many things, like if you see a room of 100 people, and if you have a small sketch, you won't be able to figure out exactly each of the people's details, but you can still recover average information, like were most of them wearing black shirts, or what is the average height of the people there. It has this graceful erasure property because it's a subspace embedding. So even if you chop off half the sketch, you still remember high level details. you get this object-oriented view and this type information where type is encoded among subspaces. And it can be used for continual learning, where new concepts produce new modules. And the way you get this continual learning thing is you have this LSH table of buckets where you store, not only record sketches, but you can also grow modules there. If you start seeing a bucket that's being hit often, then it's time to learn a new module. And you can have edges between the buckets based on co-occurrence to get a knowledge graph. So we implemented a very simplified version of this as a neural memory that can be attached to any deep network. All we did was just use an LSH table, no modules within the buckets and no edges across them. And just the contents of the LSH table can be trained. And just that itself was quite useful in increasing the capacity of a BERT model for language understanding tasks. So just by attaching a small 10% LSH table, which is of 10% of the size of the whole network, we increase the amount of computation by just 1%, and we get the same benefit as you would get by doubling the size of the BERT model. So in summary, we have a continual learning architecture, and we have a simple implementation of it based on sketching and LSH. And these are the references. Thanks.
Thanks, Reena. Thanks for the talk. Any questions for Reena?
I don't see any raised hands, so.
All right.
Yeah.
Next,
Reena, I have to compliment Reena. You came in, you had 4 seconds left. Okay, I just wanted you to know that.
Just a quick, can I ask a quick question? Can you
Yeah.
put the links in the chat, because we couldn't click on the link in the slide thing for the references. Yeah, thanks.
Oh, sure,
Okay, I
thank
can put it
you.
in the chat here. Sure.
Oh, thank you, Reena. Thanks, Cynthia.
Thanks so much.
So our next speaker is Alberto Pozzanco Lancho from JP Morgan.
So can you see my screen?
Yes.
Yes.
Okay.
Mm-hmm.
So hi everyone, I'm Alberto, and today I'll be presenting proving security of cryptographic protocols using automatic planning, which is a joint work with our colleagues at the JP Morgan AI Research Lab. So the motivation of this work is multiparty computation, which is a framework that enables different parties to perform a joint computation over their data while keeping it private. These kind of protocols are increasingly used at financial institutions, but we need to prove that these protocols are secure. There exist different methods to prove that security, and in this work, we are trying to prove the security of these kind of protocols using automated planning. So automated planning is a technique that uses domain-independent heuristic search to find a sequence of actions that achieve the goals from a given initial state. So for example, in a map navigation problem, given initial location, how to reach the destination, the goal state. However, planning can also be used to do kind of the opposite. So prove that there is no sequence of actions, so no plan exists that achieve the goals from that initial state. And for that case, we change our initial state, and now it will be the information held by each user and the parties that can be corrupted. And in the goals, we will have that the protocol needs to finish, so work as planned, and that some security properties need to be verified. And we will also have in the actions to achieve the goals from the initial state, the actions that each party can execute, so each user and the server, and also the malicious agent attacks. And after giving these inputs to the planner, the plan will return either if a plan exists, and therefore the protocol is not secure, or if a plan does not exist, in which case the protocol will be secure. So let's focus now on the protocol, on this protocol, privacy preserving aggregation protocol. So in this protocol, we have a set of users or agents. Each of them has some information that can be splitted or decomposed into multiple parts. So for example, here we have X1, and its information can be decomposed into alpha 1, alpha 2, and so on. So now let's see how this protocol works. In the first round, the user exchanges the information. So X1 sends alpha 2 to X2, alpha 3 to X3, and so on. And it also receives some information from the other users, creating this kind of metrics. In the next round of the protocol, the users sum the information and send it to the server, which computes the aggregation. And by following this protocol, the server cannot identify which is its user. So basically, the user keep their data private. And in this protocol, the malicious agent can perform the following attacks. it can corrupt an user, and therefore it will know the information of that user and also the information that user received. It can also corrupt the server, in which case it will know the partial sum of each of the users and also the total sum computed by the server. And it can also infer information. So, for example, if the malicious agent have access to these three pieces of information and the partial sum, it will be able to infer delta 1 by subtraction. So now let's see how we model this cryptographic protocol and the attacks in PDDL, which is a logic-based language that is the standard in the automatic planning community. So in PDDL, we need to define predicates that are the pieces of information we are going to reason about. So for example, in this case, we use the noun, we created a noun predicate that represents that a given share from an user is known by another user. We also have predicates like can corrupt that represents that a malicious agent can corrupt a given user. And with these predicates, we build the actions that will describe the dynamics of this domain, in this case, the dynamics of the protocol and the possible attacks that the malicious agent can conduct. And these actions take the form of preconditions and effects. So for an action to be executed, some of these predicates need to hold. And after executing the action, some of these predicates will change their truth value. So after describing the domain and the dynamics of the problem, we need to define the problem itself. So in the initial state, we will have that we will be in the first round of the first round of the protocol. The users know their own information, of course, and we also need to specify the parties that the malicious agent can corrupt. So in this case, let's say it can corrupt these three users. And in the goal, we need to specify that the protocol needs to end. So the server needs to compute the aggregation. And also we need to specify the security properties we want to verify. In this case, that the malicious agent cannot know or cannot infer the information from the user X4. And for the sake of time, I won't enter into much detail on the proof, but basically what we do is to create problems with increasing number of users being corrupted. And at the moment that the planner returns as a plan, it will mean that the protocol is not secure. So for this simple scenario, the protocol is secure up to 3 users plus the server being corrupted. And this is the plan that the error trace that the planner returns, and is the plan that the malicious agent could follow to infer the information from all the users. So wrapping up, we have shown how planning can be used to verify the security of cryptographic protocols. We have something that is quite cool in the planning community, that is that PDDL is a standard language. And this is an advantage over model checking, where each model checker tends to have their own language definition. And by leveraging on this PDDL language, we can use a wide variety of powerful planners that can usually, that are really efficient and often can detect the unsolvability of this task even without conducting any search. And in future work, this is an ongoing work. So in the future, we would like to compare against model checkers, model and prove other protocols, and check different security properties. So that's all on my side. Thank you very much.
Thank you.
Thanks, Alberto. Mm-hmm.
So next speaker is Vipul Goyal from NTT Research.
Okay, can you see my screen?
Yes.
Mm-hmm.
Okay, so hi, I'm Vipul Goyal, and I will talk about post-quantum secure multi-party computation. I'm from NTT Research. So let me first talk about secure multi-party computation. So here we have several parties, 4 parties here, and they each have a private input. And they're trying to compute some joint function of these private inputs. So as an example, maybe we have 4 millionaires, and they are trying to compute who is the richest among them without revealing exactly their net worth to each other. So this can be framed as an instance of MPC, but This is just a toy example, but MPC has many applications. So for example, privacy preserving machine learning or data mining and so on. So over the last 3 decades, MPC has been a very long and successful line of research. And initially for the first couple of decades, it was seen mainly as a theoretical tool. But over the last 5 to 10 years, it has also been moving from theory to practice. So I want to focus on the quantum analog of MPC. So a natural question is, what if an adversary acquires a quantum computer, either now or maybe not now, but sometime in the future? So there has been a sort of a boom in the study of quantum computing and quantum cryptography. So this is a very natural question. Maybe the adversary is storing all the messages in the MPC protocol. And in future, when quantum computers become more realistic, maybe the adversary will try to break and will try to sort of obtain the private inputs. So the question is, can we build MPC secure against these type of adversaries? And we call this to be post-quantum MPC. And actually, even before going to MPC, if you work in cryptography, you might be wondering about zero knowledge, which is sort of even simpler than MPC. It can be seen as a special case of MPC. So in zero knowledge, we have a prover and a verifier. And the prover is trying to prove a statement to the verifier while hiding the witness. Right? So can we build post-quantum zero knowledge? So let's say the verifier is a quantum adversary and verifier is trying to learn something about the witness from the proof. So at first, it might seem like post-quantum zero knowledge or MPC might not be very hard, right? So the area of post-quantum cryptography has seen very rapid progress over the last 5 to 10 years. So for example, now we have lattice-based cryptography, which can allow us to do all kinds of beautiful things. So there are several simple zero knowledge and MPC protocols based on sort of mild primitives or mild cryptographic assumptions like one-way functions. Or in case of MPC, it would be what is known as oblivious transfer. So the natural question is just take these protocols and the cryptographic primitive which you are using, let's say the one-way function, just use the post-quantum version of that primitive. So just instantiate this using post-quantum primitives. So does this already work? And the answer is no. And this is a very interesting problem. Quantum information behaves in a fundamentally different way. So for example, there's the no cloning theorem, which says that you cannot make copies of an arbitrary unknown quantum state. So just the way quantum information behaves leads to sort of many of these protocols becoming insecure, even if you are using post-quantum primitives to instantiate them. And if you are familiar with cryptography, let me give you a very brief sort of example of what might break down. So in zero knowledge at MPC, we typically talk about simulators which rewind the adversary. So what does rewinding even mean? The simulator will take snapshots or make copies of the state of the adversary periodically. And then at any given point of time, simulator can sort of discard the current copy or the current state and go back to a previous copy. This is how you implement rewinding, but you cannot copy arbitrary states. If the adversary A is a quantum adversary, then because of no cloning, you cannot make copies. So you cannot rewind the adversary in a straightforward way, unlike the classical setting. And this is not just a theoretical concern. In fact, there are protocols which are secure in the classical setting, but they break down in the quantum setting, even if you instantiate them with post-quantum assumptions. So in a beautiful work of Waters in 2009, the first post-quantum zero knowledge was proposed. But the progress on the MPC side, which is a generalization of zero knowledge, was a little bit slow. So in a very recent result, we were able to build sort of the first classical MPC protocol, which is secure against quantum adversaries. So the protocol and honest parties, they don't need quantum capabilities, but if the adversary has quantum capabilities, the security is still preserved. And our protocol is constant round and it doesn't use any trusted parties. If you use trusted parties, then there was some previous works already. And along the way, while building MPC, we also sort of initiate the study of various interesting post-quantum primitives. So we study what is known as post-quantum coin tossing. Coin tossing over the internet is you and I are not in the same room, but we want to flip a coin, and the coin must be fair. And we initiate the study of post-quantum non-malleable commitments, and there are many other technical challenges which one has to overcome. So I want to leave with several future directions. I think we are just sort of starting to scratch the surface here. So a very natural question is, can we build post-quantum MPC with better efficiency or with better cryptographic assumptions? Or we can move to quantum MPC. So in quantum MPC, the inputs are quantum states and the circuit can even be a quantum state. So let's say you want to run Shor's factoring algorithm using an MPC, right? So that's a quantum circuit. So can we build quantum MPC? And there are already a few works in this direction, but like less than 5 papers. And another natural direction is we can stick to classical inputs and circuits, but we can use quantum communication. So we are trying to solve an older problem, but with newer sort of tools. So one might be able to get better results by doing this. And then finally, can we come up with fundamentally new ways of building zero knowledge and MPC in the quantum setting? So far, all the works are sort of trying to take the classical ideas and trying to sort of mimic them or transport them in the quantum setting. But quantum information behaves in a fundamentally different way. So maybe, there are like completely different ways of doing simulation and building zero knowledge and MPC. Okay, so I will stop here.
Thanks, Vipul. So our next speaker is Elizabeth Barton from ROC 360.
Hi, everybody. I'm Betsy Barton. I work at Rock. Well, I work with Rock 360. I'm going to switch gears a little bit and talk about some problems relating to the U.S. housing stock and refreshing U.S. housing stock. So this is a problem where the use of technology is somewhat new. So it's kind of different from the other talks that we've seen today, but it's a very big problem. Where technology is, it's time, it's ripe for technological applications. So I think the question is, so the US housing stock is aging. About 80% of US housing is more than 20 years old, and about 40% of it is more than 50 years old. So the big question is, how do we upgrade this housing in a way that's efficient, effective, and sustainable? And furthermore, the fraction of housing with green certification is very small. Most of this housing is not environmentally very well put together. It's not sustainable. And how do we change that and improve the sustainability of the US housing stock? So technology, what is the role of technology? I'm going to just sort of survey some things that we're doing. The problem is very difficult because the market is highly fragmented. So it's the scalability of solutions to this problem are very limited right now. Flippers, housing flippers work alone or in small groups. Many people sell their homes with isolated real estate agents. There's some data available, but it's limited. So the roles for technology in the near and medium and long term are to discover the homes that need renovation, understand what in those homes needs to be renovated, which is difficult to do even if you're standing in the middle of a house, to be honest. So it's a very hard problem to do when you haven't walked inside the home yet. And then optimize the plan, the materials, the labor, and the management, which is, again, something that really has not been done to date. So outside the home, obviously, the place we can get the most data is the outside of the home. So things like drone imagery and Google Street View, and even you can physically drive by a house if you're trying to identify the houses that need renovation. So in these cases, it's obviously possible to use computer vision to identify dilapidated housing from images of roofs and outside, and understand the neighborhoods and make models about what do you think is going to happen to the neighborhoods and what the economics and liquidity in the situation are, for example. But you can't tell very much from standing outside of the home about what's actually inside of it. So this is a major problem. Inside the home, you do have data. The multiple listing service. So every house that's been on the market recently, for the most part, we have images from the inside. It's a huge amount of data. It's possible to use computer vision to evaluate the inside, the images from these houses, but there's a number of issues. So first of all, this is a very different problem from, for example, the object detection problem, because you're asking, what is the condition of this property, not what is this object? And so it lends itself to some differences. But the other thing is there's like less tangible things about, is this an updated property? Is it modern looking? Is it appealing to people? These are different types of problems than the standard object detection. NLP, so natural language processing on descriptions in the MLS is probably the easiest problem I'll talk about today, because there are a lot of clues, like things being called a fixer-upper or quaint and charming. But the fundamental problem with the MLS data is that it offers you a very biased view. You're seeing what a real estate agent allowed you to see, right? But it is the most common thing that we have inside of people's houses. So, there's a lot of work to be done in this area, but it has some fundamental limitations. Another area that I think is even newer is the idea of getting data from inside of the home in an owner-generated way. Can we convince people to give us data about the inside of their home? Once we do that, we still have the same computer vision problems with analyzing it, telling the condition, is it up to date, is it appealing to people, how big is it? So things like size, obviously nowadays our phones are capable of producing stereoscopic imagery. Can we get people to give this to us from the insides of their houses? This is a much less biased view because it's not a real estate agent deciding what to show people from the inside of your house. It's a person giving us a view of this. So this is something that we're thinking about really hard right now, and also how to use computer vision to evaluate what we see. And then inside the walls, even more sort of further out, but more important. So like I said before, you can be standing in the middle of the house and you still don't necessarily know what needs to be done to fix this house. For example, you can walk into an older house and think that it's going to cost a certain amount to renovate, and then get one of the walls down and realize you have a much bigger problem than you thought you had. And for sure, this happens all the time. So there are non-invasive imaging techniques that we're thinking about. For example, LiDAR, obviously not at visible wavelengths, that can see through walls. And, it's another example of a nascent technology that really requires a lot more development and a lot more work, but would be fantastic for use in this problem, trying to understand what you want to do inside a home and what needs to be done. So the last thing in just this sort of survey is the full optimization problem. So most of you probably know, when you go to renovate a house right now, it's not a very controlled, again, it's a fragmented process. So you have to combine a lot of different things to try to understand what you need to do. There's, what order should I, there's what should I actually do, the condition info, what do I need to do in this house? And then there's the after repair value, like what does it make financial sense to actually do with this house? Then there's, can I get the permits? What about the regulations? Then there's materials pricing and what does it make sense to put in here and what's going to be reflected in the after repair value of the house. And then green upgrades, what makes sense environmentally to actually do. Then there's the labor market, which is changing incredibly dramatically in COVID, for example, and availability of someone to manage this project. And there's management tools, and do any of them give you what you want? Are any of them scalable? How well do they work? And finally, the construction ordering optimization problem. What do I do and what order do I do it in, and how do I do it in a way that manages the labor and manages the management so that the product is doable, so that we could tell if we're on budget, is it on time, etc. So this is actually a huge optimization problem that we're making some inroads on. It's difficult to get data on a number of these things, but it's a complicated problem. So in summary, housing upgrade is a really, really important problem in the US and around the world. And housing upgrade space is ripe for use of technology in a lot of different ways. And the quest for sustainability in housing, can we upgrade houses in a way that's greener, and what makes sense to do in the most optimal way, are big problems that we're working on. Thank you.
Thank you, Betsy. Our next speaker is Udi Weider from VMware.
Do you see my screen?
Yes.
All right, thanks. So I'm going to present a nugget of our recent research at VMware. I'll tell you about Omni predictors, what they are and what they're good for. It's joint work with my colleague, Parikshit Gopalan from VMware. Adam Kalai and Omer Reingold and Vatsal were at VMware at the time when we were working on it, now in Stanford and in USC, respectively. So let's start. Okay, so I'll start with just presenting the really basic learning setting, just to set up a common framework for what we're talking about. So, the most simple basic learning task, we get samples from a distribution, we get labeled examples. So each example consists of a feature space, say the personal information of a person or the medical info, and a label, did they test positive or negative for COVID? And our goal is to compute some hypothesis, which is a function from the feature domain to say the real numbers. It doesn't have to be real numbers. And this is supposed to capture some meaningful information. We want to determine whether a person should be tested. So that would be a binary value, or what dosage of medication to give, and so on. And the question is, how do we measure the quality of the hypothesis that we computed? And the most common framework to do that is through a loss function that measures the penalty of outputting T of X, given that the label was indeed Y. So, a common loss function would be some P norm of the distance between them. And then we typically think about the expected loss. So we compute the expectation of the loss, given that the samples are taken from the distribution that we trained on. And our goal would be to minimize the expected loss. Now, we don't minimize over all possible functions. Typically, that is not feasible. So we also think about some model families. So it is some family of functions that we care about. And as practitioners, we think it's a relevant family of functions for the problem at hand. It could be typically DNNs of some given architecture, or random forests, or many other options. And then we have in mind the best hypothesis in that class. So C star would be the one that has the lowest cost. And our goal would be to compute some hypothesis that is comparable to the best within that class. And it doesn't have to be actually a member of this class. There are many algorithms, boosting kind of algorithms, that are actually producing something that is outside that class. But this is how we think about a very basic learning setting. So I've described something that we've all done many times, and there is nothing special about it. The point that I want to emphasize is that in this framework, we have to choose the loss function at the beginning. And that is important because the learned hypothesis actually depends upon which loss function we have chosen. The simplest example is, almost a degenerate example. Imagine that the model family that we care about is just constant functions. So we want to approximate the labels by a single number. And if we minimize the L2 norm, then we're actually pointing at the mean. And if we're minimizing the L1 norm, then we're pointing at the median. And it is impossible to learn the mean from the median and vice versa. And while this is a very degenerate example, it's possible to come up with more complex and more realistic examples. And the principle still holds. The learned hypothesis depends upon the loss function. And if we change the loss function, then it is not clear how to find the new hypothesis that is optimized for the new loss function. And this comes with some cost. We don't always know in advance what the loss function, what the correct loss function is. We may want to optimize for multiple loss functions simultaneously, maybe different loss functions for different subpopulations. It's some future data, future medical treatment can show up, and we want now to optimize for a new loss function that we just didn't think about when we did the learning. So in this paradigm, what options do we have? We can either retrain with a new loss function or live with our previous one. And popular libraries come with dozens of different loss functions kind of baked in because people want the flexibility around these things. So in this work, we're trying to present a new paradigm for learning that will overcome this obstacle. And we define this object that we call an omni-predictor. So an omni-predictor is a predictor that the idea is that we learn it, and then given a loss function, we can have a simple univariate transformation over the output of this predictor that depends on the loss function, but does not depend on the data itself. And it would be competitive with the best predictor from that family C for that loss function L. So in other words, what the omni-predictor does is it extracts all the predictive power of C for that family of loss functions L. And then we can learn the predictor once, and we compute the actual hypothesis when the loss function is determined. So once we determine what the loss function is, there should be a simple way to transform the omni-predictor to a predictor for that specific loss function. Now, the first thought is, why would something like this even exist? And if you think about it for a minute, then something like this does exist and is actually maybe not phrased as an omni-predictor, but is kind of known as folk or is used in practice, and that is the ground truth predictor. So let's say that we can really compute the probability of the label being 1 given a feature set X. So if we had that P star X, that ground truth, if we were really able to compute it, then you can observe that given a point X, the expected contribution of that point X to the loss function is actually dependent only on the loss function. So if we could have computed this ground truth predictor, then in fact, we would have had an omni-predictor for essentially for all loss functions and for all model families. And the main problem here is that the ground truth predictor typically just cannot be computed efficiently unless there are really very benign circumstances or very special and strong assumptions. There is no reason to think that we can per point X compute the ground truth, the real probability that that the label is 1. It does present a very tempting heuristic to use. So we have this family seed, let's say, deep neural nets or whatever, and we can compute the best, hopefully we can compute the best predictor from this family for the L2 loss. And the reason I chose the L2 loss is that it is actually minimized by the actual ground truth. So it is kind of an approximation of the ground truth with respect to this family C, or so we hope. And we can use any proper loss function, so any loss function that is optimized by the ground truth predictions. And now let's use C star as if it was the ground truth and output a hypothesis and just hope that it's good. So we hope that now this hypothesis would be an omni-predictor for this set C. The problem is that this heuristic, even though it's very tempting and it's actually being used in practice in various places, does not carry any guarantee And there are examples that I don't have time to go through where we can show that this heuristic fails. So in some sense, our contribution is to find out what predictor actually does work for this family C, and how to compute it. And in order to describe that, I have to make a very, very brief side tour. So there is another property of predictors that comes from a completely different line of thinking, that of fairness. And that is the properties of calibration and multi-calibration. So a predictor is calibrated if it is correct on expectation in some sense. So let's say we want to predict the weather for tomorrow. So, and we predict in many different cities and many places. And what we want is, let's look at all the places or all the days where we predicted that rain will fall 10% with probability 10%. We want 10% of these days to be correct for the rain to actually fall. And that should be true for every prediction that we give. So a predictor that has this property is called calibrated. And it's clearly a property that we would like. The thing is that on its own, it's very weak. So we want to require something more from a predictor. In particular, just giving the expectation of the population is a calibrated predictor, which is very benign and very weak from an accuracy point of view. But this definition could be extended to the notion of multi-calibration. So now we think of our model family not as just a set of functions, but as a set of subsets. So it's binary functions for now. And we say that a predictor T is multi-calibrated with respect to C if it is calibrated not just for the general population, but for every set from C separately when we take our distribution and conditioned it on getting samples from that particular set. And the definition could be extended for C that are real functions, but it's useful to think now as just a calibration over subsets. And our theorem is that these multi-calibrated predictors are the right predictors for our loss minimization goal. So in fact, a multi-calibrated predictor is an LC omni-predictor. So the C is the same C, the same set of models for which we computed the multi-calibration predictor. And the L, the family of loss functions for which we are an omni-predictor, is all convex loss functions. And we show that convexity is indeed required here. And I'd like to point that there are known algorithms to compute a multi-calibrated predictor under some standard assumptions, but it is not a trivial task. It requires something, some form of boosting algorithms that we call boosting by branching programs.
So Udi, I think we probably need to wrap up. I'm
right.
sorry.
So this is my last sentence.
Thank you.
I just wanted to say that it's good karma that work that was notions that were originally motivated by fairness actually turned out to be very useful for accuracy and loss minimization purposes. And there are a lot of interesting connections there that we point out in our paper. So that's the end of my talk.
Thanks, Ari. Thanks to all our industry partners for this invigorating session. I'd like to invite all of you to join the Gathertown by following the link in the chat. Since we are running a little behind on time, we'll resume back at 11:15. So it would be a Gathertown session for another 13 minutes or so. We recommend that you use your full name on Gathertown so that people can recognize you, and we'll be muting the Zoom microphones during this networking session.
Excellent. Okay. Just there you go. Hope you can all see the link in the chat. See you in